for fun, for color fun, right? See, it's blue over there, it's blue here. Look at that, it's awesome. C2. All right, you have to be able to draw C2. These are new parametric, is a new parametric curve, so you need new functions. X is 1? Yeah, because look, if you're on C2, X is always 1, isn't it? Now what about Y? T? Y is going to just move up and down, right? That's it? Stuck between 1 and 2? So why not we just let Y be T, and then let T go from 0 to, I'm sorry, not 0, from what? 1 to 2. That would work, wouldn't it? Wouldn't that work? That would work. But I need us to think about something else here. Yeah, could we do this a different way? All right, so back when we were doing vector equations of lines, remember that formula? It was like R of t equals R naught plus TV. Remember that? R naught was any point on the line. V was the direction vector. Remember this? And this would give us, it would draw the whole line. And I told you that if you wanted to draw just the line segment, that you could restrict t between 0 and 1 and use this formula. It would just draw the segment. It would start out at R naught and end at the other end. I'm going to try and use this to come up with, this is right and we could use this. There's nothing wrong with this. But I want you to see a different version, because had this line not been vertical, then this x equals 1 wouldn't have been as easy. So let's try it with this. Look at these as 2 points. Let's see. There's some red markers. Toss me a few of those. Almost took you out, son. All right, here we go. Thank you. All right, so these points, as points, they're the point 1, 1 and the point 2, 1, right? So if I come back over here, R naught, I could use, I want to start out where? 1, 1 plus t times, now I need a direction vector. So the vector that goes from here to here, which is what vector? 1, 0, right? It's the vector 1, 0. You're taking this point and subtracting this one, right? So you go 2 minus 1. And
yeah, the top is
1, 2. Oh, I see what you're saying. I see what you're saying. This is 1, 2. That changes things, doesn't it? That's what you were saying. Yeah, thank you. 0, 1. Okay, put these together, and what do you get? This is 1, and then you're going to go what? 0, so that's 1, and then this one is 1 plus t, right? This is your x, this is your y, right? Those are your parametric equations. So I can use this for C2, agreed? But I could also use this for C2. X is 1, y is 1 plus t. What's the difference between these? T here goes from 0 to 1. T here goes from 1 to 2. Either one of those would work. All right? Do y'all see the difference? Any questions? We should get the same answer either way. Which one do you want me to use, the red or the blue? Do you care? You want to do the red? Okay, let's do the red one. All right, so now I'm ready to set up the integral. So the integral over C2 is going to be this. I'm going to do it in blue because it shows up better. but we're actually not doing that one. We're doing this one. Okay, so it's the integral from 0 to 1 of 2x. What's 2 times x? Well, that's 2 times 1, right? So that's just 2. And I didn't get the square root part. I guess I should have done that, huh? Let's do that square root part here off of this. So this is the arc length. We never got that. What's the arc length of this thing? So what's the derivative of this? 0 squared, so that's 0, plus derivative of this? 1, 1 squared. That's just going to be 1, right? So really there is no, this doesn't contribute. It's just a 1. So we just get 2 dt. And then integrate that. I'll do this one, okay? I don't mind doing that. 2t, 0 to 1, and then you get what? 2. Okay, so what is this final answer? This final answer was that first integral that I did not finish, right? Plus 2. Now, there are 2 other line integrals. 2 other line integrals that we will be using. The one that I just gave you was the line integral with respect to arc length, right? There are 2 other ones. One of them is called the line integral with respect along C with respect to x, and then the other one is the line integral along C with respect to y. And up until this semester, this is the first time I've ever done this, I've always given students in the past just given them these 2 formulas, but not given them any idea of what the difference is between these 2 and the original one, the arc length one. But I actually spent some time on Friday coding up a picture for you, so hopefully you'll like it. First of all, what is this formula? How is this formula different than the one with respect to arc length?
It's in respect of x.
Okay, so instead of having that square root of all that junk there, it just has x prime of t, right? That's what it has, right? So go back to the arc length formula. Here is the arc length formula. Equals, I don't know why I did that. My question right now is how would that turn into just dx dt, which is just x prime of t? Only if that was 0, right? If that was 0, this would happen. And the derivative being 0 means that the original function was what? Constant. So this formula right here is what happens when you look at that line integral and you hold y constant. This one is what happens when you hold x constant. So let me show you geometrically what that looks like. It's really kind of interesting, I think. I think it's only interesting because I spent some time making the code for it, so it's extra interesting to me. All right, so there's my surface. This is a new problem, okay? So here's the surface. Here's that little red curve on the ground, right? Here's the blue curve up on the top. And now what I'm going to do is I'm going to go ahead and draw the curtain. Okay, so there's the curtain. If we found the area of that, that would be the line integral with respect to arc length, right? If we hold y constant, what we're doing is we are projecting that onto the xy plane. So can you all see if I turn this to the side, it would be just like a shadow, the shadow of that curtain being cast upon the xz plane. See that shadow? Let me bring it, whoa. Bring it back around. Okay, so there it was. Again, if I look at it from the top, so it's kind of like I'm drawing lines straight down, like along the x-axis there. and just using this as the bottom of the curtain instead of that arc as the bottom of the curtain. That's what it is if I hold the y constant. That's the line integral with respect to x. Let me take the surface out of there. It kind of gets in the way. All right, there we go. So there's your line integral with respect to x. Now with respect to y, it's just going to be slapped on the other plane over there, the YZ plane. So it's the shadow on the other side. Understand? Though, do these have the same areas? Like, is the area of this one right here the same as this one's area? Do they even look like the same geometric shape? I mean, look at this. Look at the curve on the top of this one, right? Compare that to the curve on the top of the other one, right? It's got this big sharp hump there, and then it comes down. So these are going to give us different areas. Do you understand geometrically what they are?
If you add both of them, would you get the area of the...
What do you think? Do you think if I add these two up, I'll get that? That's the formula for arc length, right? Yes? If I take this with respect to x, it's just x prime t, right? dt. If I add that to the other one, which is just y prime t, right? If I put these two together, they both have f in them, don't they? So I could factor that out, which would be f of xy, and then I could put in here parentheses x prime t plus y prime t dt. Understand? I'm doing these two together like that. Is this? It's not. Look, if I could take the square root of this and kill off these two squares, then they would be the same, right? But that's not the way the square root works with addition in here. So they are not going to be equal. I don't know if that helps you see it, but they are not algebraically the same. All right, let's get through this note, and I think there's another example here. The two previous line integrals often appear together in problems. So throughout the rest of this chapter, these the line integral with respect to x or with respect to y, they'll appear. And we often write them together in a single problem. So if you have the line integral along c, and instead of using f, I'm using p of xy with respect to x, plus the line integral along the same curve c of q of xy with respect to y, this is equal to this. This is just notation. If you see a single integral with a function with respect to x plus a function with respect to y, it means you split it up into two line integrals separately. But one of them is with respect to x and one of them is with respect to y. And go back to that formula. When it's with respect to x, what do you have to throw out here? The derivative of x with respect to t. When it's with respect to y, you have to throw the derivative of y with respect to t. So this piece right here is the only difference instead of the square root part. It's like what?
Partial integration.
A little bit. All right, so let's try this. Let's try the line integral along c of sine x with respect to x plus cosine y with respect to y, where c is the top half of the circle, x squared plus y squared equals 1, from 1, 0 to negative 1, 0, and the line segment from negative 1, 0 to negative 2, 3. Let's draw our c's. We have two curves here, don't we? Okay. All right, circle is the top half of the circle from 1, 0, which is here, to negative 1, 0, which is here. I'm actually going to put some arrows on it this time to show direction, that I want to go from 1, 0 to negative 1, 0. And then I'm going to run out of room. Maybe not. Might be able to squeeze this in here. Then I want the line segment that goes from this point to negative 2, 3. So 1, 2, 3. 3 is way up here. So negative 2, 3. I'll do this one in red. This is C2. This is the point negative 2, 3. This, of course, was the point negative 1, 0. Why am I labeling those points? I'm going to be using a vector function to draw that later, the line thing. So I'm going to use the points. And all right, so let's get C1. I think C1 is going to be hopefully straightforward. What's C1? How can I draw C1? Cosine t sine t? And what's my t restriction going to be? 0 to pi, right? Let's get C2. Well, to get C2, I'm going to do a little scratch work here on the side first. To get C2, I'm going to have a vector curve, a line, right? It's going to start out at what vector? Negative 1, 0 plus t times the direction vector, which is the vector that goes from here to here, which should give me what? Negative 1, 3. Taking the x coordinates, subtracting them, y coordinates, subtracting them. This should be, I'll put it all together right now. Negative 1 minus t, and then this one 0, so just 3t, like that. And that's it, right? That's my x and my y right there. And what's the restriction on t going to be for C2? 0 to 1. It's always going to be 0 to 1. Okay, so x is negative 1 minus t, y is equal to 3t, and t is between 0 and 1. All right, got my C1, C2. I think I've got those nailed down. Now let's go after this integral, this line integral. Any questions up to this point? All right, I'm going to erase the picture. So I'm going to rewrite this integral because it's important for us to see what we're actually going to do to this. This is actually the line integral over C1 of sine x dx plus cosine y dy plus the line integral over C2 of sine x dx plus cosine y dy. That's what that is, right? You have to split it up into two different line integrals. However, this notation, when you have two different integrals, one with respect to x and one with respect to y, in one integral you split it into two, right? That's the notation for it. So this actually becomes line integral over C1 of sine x dx plus line integral over C1 of cosine y dy, and then plus line integral over C2 of sine x dx plus line integral over C2 of cosine y dy. And that becomes the line integral over c1 of sine x times x prime of t dt. I guess what I'm getting at here is that this right here is what that means, right? And then what about the next part? What would I have next? Plus line integral over c1 of cosine y prime of t dt, right? And so what we're saying there is that y prime t dt is really what this means, right? And then I have two more, don't I? Okay, I'm not going to write the next ones down, but is that all right? Two more integrals. All right, so why don't we go after these one at a time, okay? Let's go after these one at a time. Let's start out with this one right here. I'll do this one, the top left corner. What is the integral over c1 of sine x times x prime t dt? All right, this should be equal to the integral. Now, we're on c1 right now, aren't we? On c1, our restrictions are from 0 to pi. So I go from 0 to pi of sine x, right? So sine of what? Yeah, this is weird. X is cosine of t, right? So this is sine of x means sine of cosine, not sine times cosine. Sine of cosine t times now x prime of t. Derivative of x with respect to t is going to be negative sine t. So negative sine t. And then dt. That is just this one, right? And then we have to do plus this one, plus this one. I'm going to do them all, I think. Maybe I'll do the first two or three. We'll see. Do y'all want to finish that? Do y'all want to calculate that, or do you want to write them all out first? What do you want to do? Use a calculator?
That'll be a basic U sub, wouldn't it?
This is a basic U sub. It works straight away. This is the U sub here is cosine t. The derivative of that is negative sine t. And therefore, this is just sine u. The antiderivative of sine u is negative cosine u. Yeah? So u, if we made the substitution, yes, and then you go back. So this is just what? What's the antiderivative of this? Cosine, negative cosine of cosine t. Negative cosine of cosine t. But then that's evaluated from 0 to pi. What happens when I plug in pi? I get cosine pi, which is negative 1, cosine of negative 1, which is some number. Plug in 0, cosine of 0 is 1, and then cosine of 1, which is some number. So we could figure that out numerically? All right. All right, let's look at this next one. This one right here. For this one, we have integral over c1 of cosine y times y prime t dt. Which is, let's see, we are on c1, so we're using this curve. So we're going to go from 0 to pi again. And we're going to do cosine of y, but what's y? Sine t. And then y prime of t, which is cosine t. So this is going to work a lot like the other one did, right? dt. So the antiderivative of that, if we work it out, should just be sine of sine t. Evaluate 0 to pi. That good? All right, let's do the third one. The third one is where we're on C2, right? I'd like to do the C2 ones. So the integral over C2 of, where is it? It's cosine y dy, right? Which turned into cosine y y prime t dt. So what is our integral going from?
0 to 1.
0 to 1. Cosine of y, which is actually cosine of 3t, times the derivative of y with respect to t, which is 3, and then dt. Antiderivative of that? Sine 3t.
1/3.
Yeah, but the 3's here, so it's okay, right? And then we go 0 to 1. Last one. Let's just finish it up. We'll do the last one over here. Integral over C2 of the last one, which was this it here? Did we just do this one? Did I do the wrong one?
Yeah, you went to the fourth one.
I went to the fourth one. Okay, this was the fourth one. The one before that should have been sine x and then x prime t dt. Sorry about that. This is the third one. That last one was the fourth one. So this is going to go from 0 to 1. Sine x, but what's x?
Ah, no, this is C2.
Negative 1 minus t, and then x prime t, which is negative 1 dt. Y'all agree? And then we could do that. I mean, we could. Right? Okay, that's how we do something like that. Y'all ready for the end of the semester?
Yeah.
I can tell. Well, you know, once Thanksgiving gets here, it's over, right? I mean, this is the worst because everyone shuts down. A week off? You get Thursday off and Friday off. Yeah. Yes. Yes. This isn't third grade where they give them the whole week off. Okay, orientation of path. What happens if we change the orientation of the path? In other words, does it make a difference to go along a curve from like A to B or B to A? Does that change the value of the line integral?
Yeah.
I mean, you could make a guess that it would. Maybe it doesn't. What do you think?
I think so.
How about if we're doing a line integral with respect to arc length? Yeah, because in the formula it's the square root, isn't it? Square root and all that? Yes? But if we go with respect to x or y, it might change it. So, no, it's because the delta x, the width of the rectangle, could be negative if you go, because it's change in x. You know, so it could be positive or negative depending on which way you're changing. So without going through an explanation of it, here's the relationship we have. Here's the connection between integrating over c versus negative c. Keep in mind, c means one direction. Negative c is the opposite direction. All right? That's what that notation means. So if you are integrating with respect to x, then integrating over c versus negative c is that we will have difference in sign. They're going to be off by a sign. They'll be the same value, but one will be negative, the other will be positive. Same thing happens when you integrate with respect to y. You have a sign change when you change directions. But when you integrate with respect to arc length, it's the same. All right? All right, path independence. Given 2 points A and B, what happens if we choose two different paths connecting them? Does it change the value of the path integral or the line integral? So now I have A and B, right? I have two different paths. I have C tilde and I have C. If I do the line integral over C tilde and compare it to the line integral over C, do you think I'm going to get different answers? Yes. Remember, it's the area of a curtain, right? So the area of the curtain is going to be different above both of these, aren't they? So in general, well, here's the actual example. Okay, this is an example that we could work through to verify. This one has us doing this line integral over C, and it has us going from negative 5,3 to 0,2 along a parabola. But then it says try and do that, go from negative 5, negative 3 to 0,2 along a line segment. And if you run both of these line integrals, if you do them, then you're going to find that you get two different answers. All right? And just because of time, I'm not going to do that one. All right? So given 2 points, what happens if we choose two different paths? In general, the line integral depends on the path. If we change the path, it's likely the line integral will change. There are some conditions which make the value of the line integral independent from the path chosen. We will address this later. So what I'm trying to get across to you right now is this idea of path dependence. Right now, in general, give you a line integral, 2 points, and I give you two different paths connecting them, you're going to get two different answers. Later, we're going to see that if something is just perfect, the path doesn't matter. You get the same result every time, which winds up being a great thing for us. We'll see. We'll see. It's going to give us, basically it's going to give us what's called the fundamental theorem of line integrals. That path independence is going to give us that. Which is like, you know how we have the fundamental theorem of calculus in Cal 2? In Cal 3, we have the fundamental theorem of line integrals. All right, line integrals in space, perfect. This is a great stopping point, but we're not going to stop. This is a great point for us to start to transition, okay, out of 2-dimension into 3-dimension. So now we're going to lose the idea of a curtain being dropped from a surface because we can no longer visualize the function. This is a common theme in this class, right? We did double integrals, we could visualize the solid below the surface, but then we did triple integrals, you can no longer visualize what we're doing, you can only visualize what we're integrating over. So same thing here with line integrals. This time, let C be a smooth curve in 3-dimensional space. Let C have parametric equations, x, y, and z, so we can draw the curve, right? Then the line integral with respect to arc length is a line integral along C of the scalar function f of x, y, z is going to turn into replace the x with the parametric equation for x, replace the y with the parametric equation for y, replace the z with the parametric equation for z. It'll go from A to B, which is our restriction on t. So same story. The arc length is this instead of the other one, right? So we added one piece to it, right? That's it, with respect to t. Or there's another way we could look at this. And this is where we're going to start to shift gears a little bit. If we can draw this curve with parametric equations, then we can draw it with a vector curve, a space curve, which means there is a vector function, r of t, which draws that function, which draws the curve. So if I replace this entire symbol right here, sorry, inside here, inside the f, then what I'm saying here, f of r of t, this is weird notation. Hold on, I've got to sneeze. It went away. Okay. This is very strange notation because what you're doing is you're taking a scalar function and plugging what into it? A vector function. What does this mean? It just means you take the components of the vector function and you replace the x with the x component, the y with the y component, the z with the z component. That's weird notation, but that's what that means. And then this, if you go back and you look, when we were doing space curves, we said what's the length of the, if we took the derivative, so what would the derivative of this be? Of this right here, of a vector curve. If we have x of t, y of t, z of t. So this is a space curve. The derivative of this would be a vector, right? It would be x prime t, y prime t, z prime t. It would be a new vector, right? But if I asked us to take the length of it, you would do square root of this squared plus this squared plus this squared, right? Which is this, right? So notice that this piece right here is just the magnitude of the derivative, right? This is brand new notation for something we already kind of understand from the previous idea in two-dimensional space. It's shorter notation. Don't you think that's a lot shorter to write than all this up here, right? All that. Okay, well, just like before, remember how we could integrate a line integral with respect to arc length, but then we could also do it with respect to x and with respect to y? Well, with space curves in three-dimensional space, you can have the line integral with respect to x, where the formula stays exactly the same, except at the end, instead of that big square root thing, it's just the derivative of x with respect to t. And then along with respect to y is just going to throw in a y prime t. And then we have an additional with respect to z, which is z prime t at the end. And just like before, if we have them all appear together, if they all appear together in one integral, it really means you're splitting it into three separate integrals and doing each one. So this is just an extension of what we just did, yes? Nothing new? Okay, we only have 3 minutes. Let's see if we can't come up in the next 2 minutes with the with C here. At least we're not going to be able to draw it because it's in three-dimensional space. It might be a little hard. But C is actually comprised of 2 line segments, aren't they? So let's try and come up with this line segment right here first. We'll call that C1, and we'll call this from here to here C2. So how could you create C1? Use the vector equation of a line, right? So R of t equals, and let's call this R1 of t so we don't confuse it with the one we use over here. R1 of t, going to start out at the vector what? 0, 0, 0. And we are going to go plus t times now, just subtract, so it's just 1, 2, negative 1. So if we put all that together, we should just get t, 2t, negative t. Right? So the x for this one is t, the y is 2t, and the z is negative t. The restriction on t is 0 to 1. Okay? So if we're doing this, we're going to have to split this into 3 separate integrals, right? and then each of those integrals has to be split along C1, C2. For C2, I do another line. I'm going to start this time at 1, 2, -1, and I'm going to go to the other one. So subtract, and you should get the vector 2, 0, 1, right? Put them together. 1 plus 2t, 2, and -1 plus t. So this is your x, your y, and your z for the C2. Yeah?
Is it going to be six
It's going to be 6 integrals. It's going to be integral over c1 of x squared dx plus integral c2 of x squared dx plus integral c1 of y squared dy plus integral c2 of y squared dy plus integral c1 z squared dz plus integral c2 of z squared dz. When you do this, you're going. Let's just look at this one real quick. C1, you're going to replace x with what? T. So t squared dx is going to be replaced with the derivative of x with respect to t. 1. So this is just going to be t squared, right? This one right here, you're on C2 now. So this is C2. So you replace x with what? 1 plus 2t, and then you have to do that quantity squared. And then you replace dx with the derivative of this with respect to t, which is 2. Integral goes from 0 to 1. Make sense? Okay. All right, we got to go. We come back next time, and we start doing line integrals over vector fields, which means that we are going to start being able to figure out the work done as an object moves through a vector field.
How many subsections are there in this thing?
I'm sorry?
How many subsections?
This section right here, the last note, I believe, is, let's see, 19. So we still have 5 more notes to go. Yeah, this is, and look, the notation starts to get pretty crazy. How many formulas did we do today? With respect to arc length, with respect to x, with respect to y,